Hi, you guys. I'm sorry that I was gone yesterday and today. I came down with something terrible and have been feverish and sore throat. And then I have to go to my sister's wedding tomorrow. I fly out. I'm not sorry about missing Thursday, but I wish that I could have been there to teach you guys about these last couple lessons. But that's why I'm making a video. Let's go. Um, So yesterday with Mr. Dunyan, hopefully he gave you the papers so that you could randomly select some data and build scatter plots and calculate regression lines. But you learned about it in a way that some of you were asking about last week, which made me really happy. You learned about it in a statistical inference way. We looked at if there is, like, we have a true population regression line right here. Okay, but if we took just samples, we could get a whole bunch of different regression lines from here. We might even be able to get like a positive one. It'd be pretty rare. But we learned about a new parameter. I love parameters, and you know, you know that already. But our new parameter that we are learning about is the true slope. And we always call it beta, which is the slope of the population regression line. Okay, that's why last week when we were writing the equation, like y hat equals a plus bx, that's why I insisted that you use a plus bx, because we have this population slope beta, but if you did one of these like smaller regression lines, this would have a slope of b. And so b is our statistic and beta is our parameter that we're trying to learn about, because that's really the point of stats. Like, a lot of people think that stats is just like describing things, which stats does help us describe things, sure. But the real point of stats is using statistics to learn about parameters. And this is our last parameter, you guys. It's beta, the true slope. Oh my gosh, it's so cool. So, you should have made a sampling distribution of beta yesterday. And that's great. Today we'll talk about like what the like how that applies to lots of things. But I do just want to talk a little bit about how to interpret the slope in terms of a parameter. So when you're interpreting slope, we always are talking about like how this number means like where the negative 1.45 in this case is referring to how much something is increasing or decreasing based on how the explanatory variable increases by 1. So when so when we're talking about slope as a parameter, like we're going to interpret this negative 1.45 not just as like its meaning as a slope, but also as a parameter. So I would say something about the population for all AP Stats students in this case. Okay, so referring to a population, really important when you're interpreting parameter. Okay, the other thing that you have to think about is that this is on average. Okay, this beta is like the average of all sample slopes. So, yeah, so it's still going to have the language of as like number of days absent increases, the final grade decreases by about 1.45. we have to talk about it being on average. For all AP Stats students, we expect that on average, as days absent, number of days absent, increases by 1, final grade will decrease by 1.45. Okay, if you want to rearrange that to a degree, you can. Like maybe for all AP Stats students, as the number of days absent increases by 1, we expect that the average final grade will decrease by 1.45. Or for all AP Stats students, we, as number of days absent increases by by 1. Yeah, you can put the we expect later. So, like, yeah, as long as grammatically it makes sense and you're using, yeah, these are like the 3 important principles. Okay, refer to population. Okay, emphasize that it's the average grade decrease or something like that. And it also has to be non-deterministic, of course, right? We're expecting it to increase or decrease, not we're guaranteeing it'll increase or decrease. Okay? And this is amazing. Part of the reason this is so amazing is just because there are some things in life that are really clearly associated, that have a strong association. Like this one has negative 1.45 for its slope. I would say it's moderately strong. I don't know what the R is on this, but I'd say it's moderate. But something that's important is knowing whether there's actually enough evidence to show whether it's going to increase or decrease. We often are just looking to see, like, is there actually going to be a positive slope or not? That's one of the biggest questions that we're going to talk about with these. Yeah, with these inference procedures. So, I think that's all I need to cover there. I'm going to move on to the next little section. Okay, so today, you guys, we have stuff. Oh, actually, before that, I want to talk a little bit about the sampling distribution for beta. Okay, so we have this parameter beta, yay, true slope. Okay, and you guys made it yesterday. You'd get this distribution, and it should be the mean of that distribution. So you have all these little sample slopes. B, 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 B. Everyone takes their own sample, right? We love a sampling distribution. And if you guys made one yesterday, then the center of that distribution should be the true slope. Okay? And every time we do statistics, we know that our sample is somewhere on this distribution, but we don't know where. And that's all of what statistical inference is about, is finding information based on what we know about that sampling distribution. Okay? So, the mean of the sampling distribution, the mean of all your sample slopes, is the true slope. So happy about that one. Okay, The standard deviation of that sampling distribution, I was going to write it all down for you guys, but it's like, well, yeah, I'll write it down for you. It's also on your formula sheet on the page where it shows like parameters and statistics, like the second page of your formula sheet. You can pull that out. And on the bottom of that page, it shows you the sampling distribution for slope. And it tells us like the standard deviation of all the B's is sigma over sigma for x, so the standard deviation just for like the x variable, divided by n. Okay, that's really cute. And then, but we're never going to know actual sigma, right? So the real standard, like the standard error that we would be using is, oh, I'm so sorry, I should not write that as sigma because it's a statistic. The standard deviation of the slopes, or the standard error of the slopes, is S over Sx. So the sample standard deviation of the x values, and n minus 1 right there. We have not talked about S very much, so this actually is a good opportunity to talk about what S is. S is the standard deviation of residuals, right? So that's just like basically the typical residual, or how far off off from real data our prediction is. So if somebody was like, interpret S, which I think that has been on your homework, but if like the standard, if S was like 1.7, then you're like, alright, I don't know what it is for the grades, but let's pretend for the grades that it's like 10, because we're predicting, or maybe it's 5, whatever S is, but we're like, if S was 5, and we're talking about grades, we're like, typically, when we predict a final grade based on how many days somebody's been absent, where our prediction is usually within 5 of the actual grade that they received. So that's what S is. There's stuff in the book about how to interpret S better. It's pretty rare to ask for interpretation of S, but the standard deviation of residuals is coming into play today. So that's right here, is the numerator of that fraction is this S. Okay? So, it's great. Excuse me. We love that. And all of that is kind of annoying. And if you look on your formula sheet, it gives us a formula for S where it's like, it takes every actual value minus its predicted value, and then you square it, and you divide it by n minus 2, and then you square root it. It's a lot of math. I'm going to tell you right now, if you're looking to do that all in your calculator right now, don't do it, okay? That's all I'm going to say. Especially because the online things that we've used for linear regression, they'll give you S, but your calculator won't give you S. So you might be able to find the standard deviation of the x values in your calculator. In fact, I know you'd be able to do that. But you'd have to go through and individually calculate every residual to get S, and then square them all, add them together, divide by n minus 2, and then take a square root. Don't do that in your calculator. I'm just here to tell you, don't do it. Don't do it. You might think I'm crazy. I'm not crazy, I promise. Okay, so we're going to use this to do some statistical inference. And there are two main statistical inference procedures, right? We're going to do a confidence interval. And we're going to do, I don't know what was going on with that star, a significance test. Woohoo! Woohoo! So exciting. So here's do absences affect your grade? We have this cute sample. We have the list of data. This is in your packet, you guys. You can pull it up. We have, here's our residual plot. Okay, and here is like our, here's our residual plot. Here's our, distribution of the residuals. And then here's our table. Here's the reason why I told you to not go calculate anything. Well, we're going to come back to that. But, yeah, it's because we have this amazing table right here. Do you see this? This is this table, which you guys have worked with before a little bit, has the coefficients. We're going to write our equation for this really quickly. We have like final grade. I did not mean to do this, like, it's fine. Your predicted final grade is 87.61 minus 1.58 times number of days absent, right? This is, you know that this one's the y-intercept because it's the constant, okay? Now, here's the thing that's really cool. It tells you, do you know what this SE stands for? I'll tell you what it stands for. Standard error. That's why just a second ago I was like, don't calculate the standard error by hand. I mean, it's cool that it gives it to you, or it's cool that, like, it shows you how it's calculated. Like, more power to them, but don't do it. Never do it. It gives you the standard error. It gives it to you for the y-intercept, and it gives it to you for the slope. But I gotta tell you, you're never going to do inference and AP stats on the y-intercept, so you can just ignore that stuff. Okay? So we have our standard error, which is great. So we're going to do an inference procedure right here, okay? We're going to construct, interpret a 95% confidence interval for the true slope of the population regression line, okay? For a number of days absent X and final grade Y. Okay, so our procedure would be, we have, I hope that you guys are saying this out loud, we have only one sample, and we are going to have to use a T interval for this. T interval for true slope. Okay, and our parameter is beta. True slope of population regression line. Okay. Our statistic is B, and we have 95 as our confidence level. Okay, so here's the conditions, and I love that they write these out for you. The scatter plot needs to show a linear relationship, and so that means the residual plot can't have that curved pattern that we talked about on Monday. If it has a curved pattern, then we shouldn't be using linear regression. We absolutely should not be doing inference for a linear, like when it's not a linear relationship, right? Here's the true linear relationship. It's not a linear relationship. Okay, so the independent is just 10%. This is, I don't know how many students there were, but I'm pretty sure this is less than 10%. Okay, the dot plot of the residuals cannot show strong outliers or skew. So if we look at this dot plot right here, we're looking at a pretty well, maybe not normal, but it's not skewed. It's pretty symmetric. Okay, the residual plot does not show a clear sideways Christmas tree pattern. Okay, let me talk about that for a second. I'm going to just come over here. Sometimes with residual plots, you get residual plots that look like this. So, like, here's our center line, where it has it gets really spread out. It starts out really close together on one end, and then it gets really spread out. Or you have sometimes, I don't like the way that they wrote this in this lesson, but sometimes you get something like this, like a football pattern. Or sometimes you have something like, it's not very common, but where it's really spread out on the ends and then it gets close together and then it gets far apart. You want consistent spread. Okay. It's bad if you have any of these things where it's like this side is really close together, this side's really far apart. On these ends, this is really close together, and then in the middle it has really far apart. This is where that like standard deviation of residuals. There's not a number, but the spread needs to be consistent. Okay, there's the spread here, really high, but really concentrated in the middle. So as we look at our residual plot here up top, it's looking good. It's not like super clustered together on one side and then spread out on the other side. So rather than say the dot plot of residuals cannot show this, like I would say has consistent spread. That's really what we're looking for. Christmas tree. Oh wait, I'm editing the wrong thing. Let me erase that. This is what we're gonna cross out. There's a shows consistent spread. The Christmas tree pattern is not, shockingly, statistically rigorous language. Shows consistent spread. Okay, so the general formula, you guys know this. It's stat plus or minus critical value times standard error, right? Okay, the specific formula would be beta plus or minus, I'm so sorry, it's not beta. We don't have beta, silly Miss Sadler. We just have a statistic. B plus or minus T times, and then I'm just going to, the way they notate it on the formula sheet is S sub B. Okay, now, this is the great part. We have to, well, for this, we're going to show our work. Our B was negative 1.58 plus or minus. Okay, now we need to figure out our T value for the interval. Now, some of you might be like, Miss Sadler, there's a T in that table. That's not the T for the confidence interval. The confidence interval T is going to be based on what confidence level we're using, right? So we're going to ignore, right now, we're going to ignore these things. We're just going to use the standard error. The T value that we need is going to be from degrees of freedom of n minus 2. It just is n minus 2. I mean, I don't want to, if you think about, where, you know what, degrees of freedom are degrees of freedom. I'm not going to go into it a lot. But it's a 2-variable data set, and that's how I remember that the degrees of freedom are n minus 2. I've forgotten my sample size, so I'm so sorry. We did take 10 students. Okay, so our degrees of freedom right now is 8. So we're going to go to our T table that you guys all have in your formula sheet, and we're going to go to 8 degrees of freedom and look for 95% confidence. We're going to go up there. So 95% confidence for 8 degrees of freedom should be 2.306. 2.306 times, and they gave us the standard error. 0.3. Okay. So you can calculate that standard error, or that confidence interval right here. I actually meant to calculate this before and didn't. 1. Yeah, okay. Actually, it's... Well, no, it'll just take me a second. Okay, the confidence interval you should get should be... all clear. 9.58. So, should be like a negative 2.27-ish to... negative 0.888. That's what I got. If I did my math wrong, I'm sorry. Okay? So, we could say, hey, we are 95% confident that the true slope of the population regression line for number of days absent and final grade is in the interval negative 2.27 to negative 0.888. Okay? What does that tell us? Here's my question. What if I came into this with the question, is there actually a relationship between number of days absent or not? My sample of 10 people shows one, but do I think there actually is one? And this tells us, or what if I ask, is there a negative relationship? You would have to say, like, we are, because this interval is negative, we have significant evidence that the true relationship has a negative slope. Yeah, it really does decrease. Well, we expect it to decrease on average your final grade when you're absent more. Shocking. Wow. That's crazy that being gone a lot would decrease your grade. So the conditions here, you guys, are a lot. In my experience, I can't, like, if they put this on the AP test, this unit is like usually 2 to 5% of the test. So it's not a lot of the test. That's why I'm only spending like 2 days on it. But if they were asking, they might ask a multiple choice question about it. Where they ask about like, would it be reasonable to do an inference procedure with a residual plot that looks like this? Or they might say, has this met the conditions? Okay. Oh, I didn't even talk about the random condition. It should have been random. But these are the conditions. Linear, independent, normal, equal standard deviation, and then random. Okay. Yeah. Yeah, in my experience, they don't ask a lot. Again, this is like 5% maximum on the test of multiple choice questions. And usually, if they have inference about slope in the free responses, it's short. Okay? Okay. Then we can also do a hypothesis test. So if you look at like the next day, here's like all the stuff. I could Okay, I just want to skip ahead. Well, let's look at the residual plot. Would it be reasonable? Yes. Here's our spread, super consistent. Here's our residual, like, dot plot, and that shows us a pretty symmetric thing. Okay. So it's looking good for inference in our conditions. Okay, so is there like evidence for a hypothesis test? So we can do a one sample t interval, or not t interval. Okay, one sample t test. For true slope. And beta would be our parameter, true slope of, and our, well, let's write our hypotheses, okay? You can have other hypotheses, but let's look at the table up here again. Do you remember when I was, like, talking about, okay, here we have our coefficients, that's, like, our actual numbers, and then I said, hey, don't worry about any of these things for the constants, because that doesn't matter. If you'll notice, we still have we have the standard error. Right here, here's our standard error, but then we have a t, and we have a p. Okay. It is actually a t-value, a standardized test statistic, and a p-value for a test. But something that's really important is this line assumes that our alternative, or that our null hypothesis is that the true slope equals 0. If you have a different null hypothesis and alternative hypothesis, and that the alternative is not equal to 0, we're assuming there's not a linear relationship, and then checking for if there is one at all. And that's what our p-value is. That's right there. Okay, so that's something that's important, is the table, at least, gives us these values based on these hypotheses. If you wanted to do a different one, you'd have to ignore these and just use the standard error, which is fine. That's fine to do. But if you're using these, I did not mean to do that. If you are going to use these values, you're going to have to have your hypotheses be exactly this. Our H naught is that B equals 0, and our alternative hypothesis is that B is not, or beta, I should say, is not equal to 0. And I should define beta. Beta is the true slope of the regression line between, in this case, absences and final grade. Okay, so our significance level is 0.01, and our statistic is 0.328, and this is positive, so we have some evidence that there is a positive linear relationship. But do we have significant evidence? It's a good question. We checked conditions on the last page if you did the whole thing, so we're going to ignore that. So the general formula for this is, I'm just going to zoom out a little bit so I can keep things, would be our stat minus our parameter divided by our standard error, right? So that's our slope minus our slope from our hypothesis divided by the standard error of slope, which would be 0.328 minus, we're assuming 0, over 0.05. So if you you do the math, 0.328 divided by 0.05, you get 6.56. Okay? Now they calculated that for you, the p-value from there. So here's the 6.56. They calculated the p-value for you right here, which is amazing. Okay. So good. So, and that, like, on a T chart, or a T table, I mean a T graph, we would be so far above here that we'd get this, like, really small shading here. So our standardized test statistic is 6.56, and our p-value is, you could, if you're doing a hypothesis that's not zero, what's the word, that's not with the null hypothesis that it's equal to 0, and the alternative hypothesis that it's not equal to 0, you would have to do, you'd have to use the t-table to go look up the tail probability again, which is a good little thing. Remember, our degrees of freedom are n minus 2, but our p-value is 0.000, that's 4 zeros, 64. So, make a conclusion in the context of the problem. So, because our p-value, because 0.000064 is less than alpha of 0.01, do we reject or fail to reject? Reject our null hypothesis. We reject our assumption, right? Again, we were assuming that the true slope was 0, that there's not a linear relationship, or that it would have a slope of 0. So we have convincing. Oh my gosh, wait a second. I'm just realizing this is a positive thing. Sorry, it's the time studied. I'm so sorry, I got my context. Convincing evidence that there is a positive relationship I should say a positive linear relationship between studying and probably time studying and grade. I probably could have done better at that context, but I don't want to go back up and check on it. But you guys get the idea. And I know when I introduced these tables to you last week, or on Monday, no, I think it was last week, you're like, there's so much stuff, it's so annoying. It's not so annoying. They're just giving you all the information that you need to do a hypothesis test if you're assuming these things. Amazing! You guys, we love it. Okay. If there's time, work on the check your understandings for both of these days, just so you can get a little feel for inference, for slope. Okay, you guys got this? And I will see you on Monday.